Hey PKL class, we're going to take a look at the notes for section 3.4. We're going to be looking at concavity, and that's going to involve the second derivative. And then there's also a specific test called the second derivative test, which actually does the same thing that we've already done, which is locating mins and maxes, but it's a different way of doing it with the second derivative. Okay, so to start, what we need to discuss first of all is concavity and what exactly that means. To me, the simplest way to describe what concavity looks like when we're looking at it on a graph is the graph curving downward or is it curving upward? Now, when I say that, it doesn't necessarily associate with just increasing and decreasing. You can have a graph that's decreasing and yet it is curving upward. So let me try to explain that. So if we look at this graph, 1 over x minus 1, throughout its entire domain, this function decreases. It's decreasing. If I start out here at negative infinity, it's decreasing, 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 and we see that there is a vertical asymptote at x equals 1. But as we start the function up again after that, we're still decreasing the entire way. Okay, so this function decreases on its entire domain, even though there's a part of the domain that's excluded, which is at x equals 1. However, the concavity is different. The concavity of this graph is concave down from negative infinity to 1. It's curving downward. It's cupped. The cup shape is pointing down. Is another way I can think of it. Think of it like if you're trying to hold a liquid in there. You know, it would dump out here. The cup is down, or it's curving down. Now in this part of the graph, even though it's still decreasing, it's curving upward, we would say. It's curving up, and the cup is facing up. Okay, so hopefully you can visualize the difference between concave up, concave down from that graph, and to distinguish between the fact that decreasing doesn't necessarily mean concave down. It can, but here we're also decreasing and we're concave up. All right. Okay, so it says definition of concavity. Let f be differentiable on the open interval I. The graph of f is concave up on I if the first derivative is increasing. Okay, so if the first derivative is increasing. Okay, so it's like what we want to be looking at then for second derivative is whether, you know, because the first derivative is increasing, then the second derivative would have to be positive, right? Because the slope of the tangent line on the first derivative would be positive. Okay, and it's concave down if the first derivative is decreasing. Okay, so that's why when we do our tests for concavity, we're actually looking at the second derivative. So if the second derivative is positive in that interval, then the graph is concave up, because first derivative being increasing would mean that the second derivative is positive. So the derivative of the derivative would be positive. Okay, and then for concave down, we would see that the second derivative is negative because the first derivative would be decreasing on that interval. Okay. So for finding concavity, we look at that second derivative, and then we test for positives and negatives in those intervals. So the definition of a point of inflection. So a point of inflection, things that you can abbreviate it, POI, is an ordered pair where the graph changes concavity. Okay, so to locate points of inflection, what we need to do, it says if C, f of C is a point of inflection on the graph, then either the second derivative was equal to 0 or it did not exist there. So that's what we do first. Now that doesn't guarantee that it's a point of inflection, but if it is one of these two things has to be true. So what we do is we find the second derivative and we find its zeros, and then we also find where it might be undefined if it is, and then we test those x values and see if the concavity changes on either side. Okay. Okay, so in example 1, now I did leave these worked out. What you're going to find, I think, on some of these is it's a real good review for finding derivatives in some of because that's probably the most tedious part, is going through the derivative process, especially on some of these that might involve chain rules and quotient rules. It gets to be a lot of algebra and simplifying. So I left it worked out. We'll talk through the steps here just to save time on the video. Okay, determine the open intervals on which each graph is concave up or concave down, and then state any points of inflection. Okay, so for this function right here, we could use a quotient rule, but to me, because there's just a constant in the numerator, I think it would be easier to bring this x squared plus 3 up to the numerator and call it to the negative 1 power. That way I can just use the power rule with a chain rule, which I think is easier than the quotient rule. So that's the way I reset it up like that. So no derivative involved here, just rewriting it. Now I can use the power rule, multiply that -1, so it's -6x squared plus 3 to the -2, but then the chain rule is involved because I have to take the times the derivative of that piece, which is times 2x. And then as I simplify that, 2x times the -6, I get -12x times the x squared plus 3 to the -2. So that's my first derivative. So sometimes these, especially with rational functions, sometimes when you do the second derivative, the functions get simpler with polynomials. With these ones, they tend to get more complicated. So it's a little bit messy, but what we're going to do here again, I'm going to leave this negative exponent. I'm going to have to use a product rule this time, right? And this one I didn't need to because it was just a constant, but now I've got an x there. So that means it's something other than just that constant. I have to treat these as two separate functions, okay? So I have to do a product rule here. So derivative of the first, -12, times the second, that's what I'm doing there, plus the first, -12x, times the derivative of this second piece. Now when I do the derivative of the x squared plus 3 to the -2, I have to involve a chain rule, so I'm going to bring my -2 and multiply that down. That's what I've got right here. And then times x squared plus 3 and take one away from the exponent. And then the chain rule again times the derivative of that x squared plus 3, which is 2x. Okay, so when I multiply my pieces together, that's going to give me 2x times -2 times -12x, which is going to end up being positive 48x squared. And now I'm going to put this back down in the denominator with a positive exponent, the x squared plus 3 cubed there. And then same thing here, I'm going to put that back as a fraction. Because in order to solve this now, I think we need to get rid of those negative exponents. We want to make our fractions again. And then when we solve our rational expression, we just find zeros of the numerator and the denominator. But before we can do that, we need to get a common denominator here. So there's just all kinds of calculus derivatives here. Now there's lots of algebra to simplify involved right here. And so to do that, I have to multiply x squared plus 3 so that I have x squared plus 3 to the third power as both my denominators. So up here, after I do that and I've combined, so multiplying x squared plus 3, this is going to become -12x squared minus 36. And so when I put that together with the plus 48x squared, that's what I've got up here. And now it's x squared plus 3 to the third power in the bottom. And I can combine the -12x squared, the plus 48x squared, and get 36x squared minus that 36. All right, so now I've got it as simplified of a second derivative as I can get it. And now I want to find the zeros of the numerator, because that's where f double prime is equal to 0. And then I also want to find zeros of the denominator, which would be possibly where it does not exist if there are real solutions to that. Okay, so setting 36x squared minus 36 equal to 0, I'm doing that here. Hopefully you can see that's just going to simplify down to x squared equals 1. So I get plus and minus 1 as possible x coordinates of inflection points. Okay, and then on the where it's going to be undefined, I can see that there are no real solutions there because if I were to cube root both sides and then subtract 3, I'd end up with a square root of -3, and so we're not going to give imaginary. We're working in the reals when we're giving these on the graph. Okay, so just plus and minus 1 are the values that I need to plug onto I'm going to put those on a number line, and then I'm going to test in these intervals to see what the concavity is and if that concavity changes. Okay, so that's why I'm putting -1, +1 here. And then I've already shown my work here, I've already shown the answers, but how do we come to concave up in this interval? So what we need to do then is, okay, so we're going to test f double prime, that didn't come over, it's just f double prime right there, of something in this interval. So I just picked -2, something to the left of -1. So when I would plug a -2 into my second derivative, because that's how I'm testing the concavity, if I plug that in there, I would see, if I put -2 here, I'm going to get, positive 4 times 36 minus, that's a positive number in the numerator. And then also in the denominator, I have to get positive numbers here because I'm squaring and then I'm adding, so I can't get negatives there. So it's a positive over a positive, that's positive. Okay, so when I test and I get a positive value in my second derivative, that means I've got my graph of my function is concave up in that interval. Okay, so then between -1 and 1, I'm picking 0 as a test point. And if I plug a 0 in here, that leaves me with like a -36 on top. And then I'm always going to get a positive on the bottom, negative over positive, that's negative. So in this interval, it's concave down, So I'm going to put a negative there, concave down when I'm testing here. And finally, I'm going to test a positive 2, something for this interval, and it'll work out similarly as the negative 2. So when I put the positive 2 in there, I get a positive on top, a positive on the bottom, concave up there. So as it appears, this is what I've got. I've got, concavity changing at these zeros of our second derivative, okay? So the two things I'm supposed to do in this problem. I'm supposed to determine the open intervals on which the graph is concave up and concave down. So I'm stating that down below. We can see from negative infinity to -1, that's concave up. And then also from 1 to positive infinity, it's also concave up there, okay? And then where it's concave down is just between -1 and +1. Now, to actually find the inflection points, because we do see concavity is changing at -1 and at +1, then to actually get the point on the function, then we want to plug those values back into f of x, back into the original. So when I put -1 in here, I'm going to have 6 over -1 squared, which is 1 plus 3, that's 6 over 4, and simplifying down to 1.53 halves, okay? Same thing you're going to get when you plug in the positive one, because we're squaring it. We're still going to get 6/4 or 3 halves. So those ordered pairs are my actual points of inflection, but you got to go back into the original with, these zeros of your second derivative, and seeing that the concavity changed there. Then you're like, okay, inflection points are occurring at -1 and +1. What are the actual ordered pairs? Take those and put them back into the original, okay? And then stating the open intervals on which you're concave up and down. So you can see there is a lot of work involved here to do this whole process, but that kind of takes us through, the whole concept of second derivative and concavity and points of inflection. I do want to just give you a quick look at the graph of this function and just see that kind of corresponds to what we're seeing with where the concavity is changing. So this was our function. I put it in y1 right here. I have a different one, y2, but I shut that one off. So if we graph this, so what we should be seeing here is that, it's curving up, it's concave up from -infinity until we get to that, x coordinate of 1, and then hopefully we can start seeing, it's flattening out and curving down, right in that interval from -1 to +1, and then starting to cut back up again or curve up from 1 to infinity, which is what we saw happen when we tested those intervals. Okay, so the graph does kind of verify what we saw here when we did it analytically. Okay, all right, next one, and unfortunately this one doesn't get any easier. This one's probably, the second derivative becomes a little bit trickier just because we do have to involve the quotient rule twice in this one, which is a little bit tedious, but let's walk through it together here. So yeah, we can't really, it's not going to help, I don't think, to move this up and use a negative exponent just because we don't have a nice easy constant up there. So I'm just going to apply the quotient rule. So remember, low d high, so that's my x squared minus 4, derivative of low is 2x. Low d high minus high, and then d low, derivative of the low is 2x again. And all over the square of what's below, so I got the x squared minus 4 squared. And then if we kind of clean this up a little bit, I didn't show all the work just because it gets to be a lot of extra scratch work here, but we're just going to distribute the 2x through there, and we're going to distribute the minus and the 2x through here. And as I do that, what happens is I'm going to have, I'll have 2x squared as this leading coefficient, and then I'm going to have, or actually, I'm sorry, it'll be 2x cubed for that leading coefficient. This one's going to be negative 2x cubed, and those cancel out. And then the next terms are going to be negative 8x here, and then this would be negative 2x. And when I combine those, I get negative 10x. So the cubic terms canceled out, but the linear terms combined there, and the denominator is the same. So now I've got this expression, and I have to apply the quotient rule once again to get second derivative, which I'm going through here, low d high minus high, d low, and when I do the derivative of low, there's a chain rule involved, so bringing the 2 down, and then the x squared minus 4, and then times the derivative of that again is another 2x there. And then cleaning that up, so when I multiply out these terms, I've got a negative 10x and a minus there, so those kind of become a positive. And multiplying it all out, I end up with plus 40x to the 4th minus 160x squared by cleaning all of this up on that second part. I had to FOIL this out, and so that gave me x to the 4th minus 8x squared plus 16, and then I had to distribute the negative 10 through that, and that gave me three terms here. I'm looking to combine those with any like terms from the second part right here. And the 40x to the fourth and the negative 10x to the fourth became 30x to the fourth. I've got the 80x squared and a negative 160x squared combined for the negative 80x squared, and then the only constant was the negative 160, which is still there. So here's my second derivative. Like I said, there's some tedious work involved there, so just be careful with it. Try to work through and follow the steps, and just do your best with that. There isn't, it's good to do this, and it is. I understand that it is. There's lots of chances to make a small error in there. Try to do your work as neatly as possible. Understanding the main concepts of how to do it is very important. But again, doing your work carefully and neatly is going to be a key to getting a correct answer here. Okay, so now at this point, second derivative, we have it. We're going to find the zeros of the numerator and zeros of the denominator. Okay, and so with zeros of the numerator, I see they all end in 0, so I'm just dropping those off. I could divide both sides. I'm going to set it equal to 0, simplify it by dividing everything by 10. And as I do that, I have, now the reason I didn't solve, it factored out into 3x squared plus 4 and x squared minus 4. This is going to give me imaginary solutions because I'd subtract 4, divide by 3, and square root to be a square root of a negative. Here I get plus and minus 2. As it turns out, those are the same zeros I would get when I would plus and minus 2 if I were to solve this denominator, setting it equal to 0. So plus and minus 2 are my only possible, points of inflection for the x coordinates there, right? So when I put the negative 2 and the positive 2 on my graph and I test, in my second derivative, what I find is when I test negative 3, I get a positive value, concave up. When I test 0, I get a negative value. And remember, I'm testing in the second derivative, so I'm testing it here. And so you'll just have to probably use a calculator and plug stuff in and just see what's happening there. And then with a positive 3, and I test that, I get concave up again. So these are my intervals of concavity. So what I'm seeing is that, we're going to say it's concave up from negative infinity to negative 2, and then also the interval from positive 2 to infinity is where we're concave up, and we're concave down just between those negative 2 and positive 2. Okay, now, so that would almost lead us to believe that we have inflection points at negative 2 and positive 2, because it's concavity is changing there. We do need to take a little closer look, though, as well, because what's actually true if you look at the original function, as it turns out, where that concavity changes, the function is actually undefined there. So we can't have an inflection point if there is no point on the graph. If I put in negative 2 or positive 2, that's where there would be a vertical asymptote on the original function. So we can have changing concavity, but concavity can change where the asymptotes appear in the original graph. So in this case, there are no inflection points. Okay, so no inflection points here. We have changing concavities, but no inflection points, just because where the concavity changes, there actually aren't points on the graph. And I'll just verify that. I mean, you can probably believe that just based on looking at, oh yeah, it's undefined there. If we were to quickly take a look at that graph, which I had entered here, let me turn that one on. That one didn't, oh, there it shut off. Okay, so let's look at that one. And yeah, so we can see at 2 and negative 2, yeah, we're concave up. That looks right, concave up. We're concave down between negative 2 and 2, and we're back to concave up. But because there isn't actually a point on the graph at negative 2 or at positive 2, we don't technically have inflection points, but we can have a change in concavity where, when we change over, when we go across a vertical asymptote, I guess. Okay, so that's the results of all of our work on that part B that we just did. We can find the intervals of concavity, no inflection points. And then there's an easier one for part C. If we just have a polynomial, that definitely makes the process of finding the first and second derivatives much easier. Okay, so our f prime is going to be 4x cubed minus 12x squared, and then our f double prime is 12 x squared minus 24x. And solving this should be not so difficult. So if I set it equal to 0 and I factor out my greatest common factor of 12x, I'm left with x minus 2. And so the possible x coordinates of the inflection points would be 0 and 2. Those would be my solutions. And so when I put those onto my number line, 0 and 2, and if I were to test f double prime of something in this interval, like -1, and then I would test f double prime of probably 1 in the middle, and f double prime of, let's go 3, just to see if they're positive or negative. And let's just see what that would make sense here. So if I were to put a -1 in here, that would be a -12 times a -3, negative times negative, positive. So this gives me positive, and so I know that this is going to be concave up in this interval. If I put a +1 in there, positive 12 times a -1, so this is going to be negative, which is concave down in that interval. And putting in a 3, that's going to be positive times positive, so that would be positive, concave up. All right, so I've got my intervals of concavity. So for concave up, I'm going to say we are concave up from -infinity to 0, and then also from 2 to infinity. Those would be where I'm concave up. Concave down between 0 and 2. And these x coordinates are, there's nothing undefined here, so those are definitely points. They will be x coordinates on the actual function, so we should be able to state these inflection points. Okay, so our inflection points here are points of inflection, inflection points, all the same thing. So 0, let's find our y coordinate for that. If we put in 0, we're going to get 0, so that's pretty easy. And if we put in a 2, what do we get for that? So 2 in the original function. So that's going to be 2 to the 4th power is 16, and 2 cubed is 8, times 4 is 32, 16 minus 32 should be -16 for that y coordinate for that one. So there we have all of our information that we need. Okay, and that's all I'm going to do for this video. We're going to talk about second derivative test in